Okay, welcome to Units Part 4. Hopefully this is our last Units presentation, last day of the Units. We'll have some more things that's similar to it, but hopefully we'll get through the rest of this today. So, first thing we'll talk about is work. Work has the units of force times displacement, so it can be units of Newton meter or foot pound, and that is the base unit. Or I say not technically the base units because we're not in kilograms and seconds and meters, but even though it is closer to the base unit because we have our force is in newtons. Technically, again, that's not a base unit, times the displacement. But probably the more common thing you're going to find is going to be something like a kilowatt hour or horsepower hour. Kilowatt hour is very common. You'll get that on your electric bill. So for SI units, we actually have another unit that we use, which is the joule, and it's actually exactly equal to 1 newton meter. So 1 newton meter equals 1 joule. It's pretty nice. A joule is a really small unit, but mostly just because the newton is a really small unit. But the joule is definitely it's nice to have because we don't get this newton meter confused with newton meter, which is torque, whereas in British gravitational we can because they're the same unit. So we also can get torque work from torque and some angular displacement. Not very often that we do that though. How much work is required to lift 2,000 pounds to a height of 10 feet? It's a super easy question. But we have 2,000 pounds is going to be our force times a distance of 10 feet, and we're going to get 20,000 foot-pounds of work. I'm not sure why we have a little extra mark down there, but we have the units of power. So power is just work divided by time. So it's going to have units of, we just talked about work having the units of foot pound. Then we're going to divide that by time. So foot pound per second or Newton meter per second. Or we could say joule per second. Okay, but a joule per second is actually just going to be equal to a watt. A foot pound per second divided by 550 gives us 1 horsepower. Horsepower is the unit of power that we use for British gravitational. Watt is the unit that we use for SI. So let's break down the units just a little bit. I sort of just did that, but we have power divided by time. We can also get force times velocity. So force would be like Newton times velocity, like meters per second. Again, we get Newton meter per second, which is equal to a watt. We can also get torque times angular velocity. This is a more common one to use, torque times angular velocity, instead of torque times angular displacement. But your angular velocity must be in radians per second. I don't know how to stress that, but it has to be in radians per second. If not, there should be some conversion factor. But the way this would work out is we have Newton times meter time, and that's your torque, Newton meter, um, times radian per second. And radian is actually a dimensionless unit, so our units end up being Newton meter per second, and that ends up being again a watt. That's dimensionless. It's important that you have it in radians per second. We can do that again, but with our foot pounds of torque times radians per second, angular velocity, and angular radians per second. But we do have to have this 550, of course. So we divide by 550 and we get horsepower. There's a couple of useful equations. We have electric horsepower, voltage times wattage. We really haven't talked about voltage and wattage, but we have volts and amps. And this should really read current. Voltage times current. So voltage, so 1 volt times 1 amp equals 1 watt. If we divide that by 746 or 745, depends on how you round it, we're going to get horsepower. This is electrical horsepower. Mechanical horsepower, we have our torque in inch-pounds times angular velocity in RPM divided by 63025. This is just a conversion factor. So again, this was our angular velocity. This was our torque. Alright, how much horsepower is required to lift a load in the previous example in 4 seconds? So let's go back and look at that previous example real quick. There we go. So we have 20,000 foot-pounds. That's our work. So it's saying how much power would it take to lift that in 4 seconds. So next. So our work equals 20,000 foot-pounds. Our time is equal to 4 seconds. So power is just equal to work divided by time. So 20,000 foot-pounds divided by 4 seconds equals 5,000, and of course then we have to divide by 550. I could do the 5,000, but then dividing by 550 was unfortunate. So then we divide this by, that's going to be in foot pounds per second, and then so we take 5,000 foot pounds per second, and then we divide by 550 to get to horsepower. So 9.09 horsepower. Alright, efficiency. So we have a machine that's got, most machines have some sort of friction in them. They have resistance. So for example, if we have a gearbox, there's some force that's required, or some torque required to move that gearbox. So most of the time, our power input to some system is gonna, it's not most of the time, all the time, power input into a system is going to be greater than the power that's output by the system. And that's because every system is going to have some sort of efficiency involved. Unfortunately, laws of thermodynamics basically say that all energy is going to eventually move toward heat, to the energy of heat. So if we have mechanical energy, that mechanical energy will be converted into heat. At least some of it will, even when it's being transmitted. So, and again, that's because of friction. So to find efficiency of a system, we look at our power output and divide it by our power input, and that's going to give us some number. That number's always going to be less than 1. Okay, this is really important. You never get more power out than you put in, right? If you do, if for some reason if you have a way of getting more power out than you put in, come see me. We'll definitely make a lot of money off of it, but that's impossible. Physics doesn't allow for it. So another way you can get it is work out divided by work in. Okay, we use the Greek letter eta to denote efficiency. So we have an electric motor here. It assumes 500 watts to apply a 1,000 Newton force to an object at a rate of 0.45 meters per second. What's the efficiency of the system? Well, our power that's input is 500 watts, right? Power out is going to be equal to our 1,000 newtons times our 0.45 meters per second, and we're going to get should be 450, I believe. 450 Newton meter per second, or 450 watts. So then we do our power out divided by power in. So our efficiency equals power out divided by power in, and we get 500 watts divided by 450 watts, and we get 0.9, or 90% efficient. So there's some more units that eventually you'll probably come across. We'll talk about these two right here. Let's see here. Yeah, I've always been horrible at making these little things here. This is 261. And these you're going to get in EMT 110 and 210. So you'll learn about those as well. But there's lots more units you're going to come across. Most of these units are all going to be derived from our base units. In some other cases, it's pretty complicated, but for the most part, it's if you've got the base units, you got these units down, in a lot of the units you're going to come across, you should be able to recognize now. So if you have any questions, let me know.